In this lecture, we will introduce the notion of interrupts. This lecture will not be a comprehensive discussion of all of the interrupts on the PIC microcontroller, but will give a general overview of some of the interrupts available on the PIC16F887, and will introduce the different registers that are associated with those interrupts. So the first question you might ask yourself is, what is an interrupt? Well, an interrupt is a special event that you want to handle right away. So normally we think about executing code line by line by line and just going one line to the next. But occasionally there are special things that you want to handle right away. So if there's water spilling in the floor and you need to stop what you're doing and go pick that up. If there happens to be an emergency situation and you want to stop and fix that, or address that, or check on that, that would be something that would interrupt your normal workflow. But also, there may just be a time when you want to know when some process is finished, you want to know when some other message is coming in, and those types of things are good to configure using interrupts. So when an interrupt happens, your code stops executing right where it is, and it goes to what is called an interrupt service routine, or ISR. And that interrupt service routine is designed to handle whatever the interrupt happens to be. And as we'll talk about, there are several different kinds of interrupts, and those are all going to be handled in quite different ways. And then after the interrupt service routine completes, it goes back to where the code was running before. So the interrupt service routine can be thought of as a very specialized subroutine. However, instead of that subroutine being called using a call command, what happens is that particular event triggers it, and then it still returns just as though that subroutine were called from whatever line you were executing whenever the interrupt event was triggered. So here's an example of what might happen. If we were in a traditional classroom and there was a fire alarm that would go off, or if you happen to be watching this video on the internet and your fire alarm goes off in your home, what would you do? Well, you would hopefully stop listening to my lecture and get yourself out of the building and to safety. I don't want anybody to risk their lives just to learn about interrupts. So if you did have that kind of an event, what would you do? You would evacuate the building if necessary, and then once the all clear happened, you would come right back in, and hopefully you would pick up where you left off and continue the lecture. So the fire alarm can be thought of as an interrupt event. Under normal circumstances, you would just watch this video from beginning to end, or you would watch a lecture from beginning to end in class. But if there were some kind of a special event that needed to cause us to cancel class, let's say we had an adverse weather condition or something like that, that would interrupt our normal workflow, and then once that event subsided, we would be able to continue with business as usual. So let's talk about the interrupts on the particular PIC that we are using in this class. We're using the PIC16F887, and that PIC has 17 different interrupts available. And so we'll talk a little bit about several of those in this lecture, but the others we will largely touch on when we get to those particular features of the microcontroller. So each interrupt has to be set up individually. So you have to turn on or off the different interrupt types. So if you want one particular type of interrupt, you have to set an enable bit for it. If you don't want that, then you can turn off that interrupt enable. And there's also a global interrupt enable, which has to be set in order to use any interrupts at all. And so there are a few that we're going to talk about. The RB0 is an external interrupt. The PORTB Change is an external interrupt on any of the pins of port B. And then the timer 0 overflow is a timing-based or counter-based interrupt. And then there's 14 other peripheral interrupts, which we will just touch on at this time and get into more detail about later on. So what happens when an interrupt occurs? Well, your code stops executing right where it is. There's a flag that gets set, and this flag is very important because you go to the same location in code. The interrupt service vector is located at memory location 4 no matter which kind of interrupt you have. But the flags get set to tell us which type of interrupt has occurred. And so if you have an interrupt and the timer 0 interrupt flag is set, then you know that the interrupt came because the timer 0 overflowed. If another flag was set, then you would know the corresponding interrupt was triggered. Otherwise, you don't necessarily know which interrupt was triggered unless you happen to have only enabled one. But in most sophisticated programs, you want several different interrupts to be capable. So you could think about, let's say, a vehicle. There may be several different warnings that you want to be able to execute to interrupt the normal display settings on a vehicle. So if you think about a modern vehicle, it might have a lane keeping system. So if it detects that you're outside of your lane, then it interrupts you with a beeping noise or something like that. You might also have some kind of sensor in the back that indicates that you might be backing up into something, and so you want that to beep when you're getting too close to something. You might also have something connected to your fuel line. Most all of us have a fuel gauge, and in most modern vehicles there's some extra light that goes on or some message that goes onto the display that indicates when you are low on fuel, and so that might be a condition you'd want to interrupt from. So that flag gets set, and then all the other interrupts are disabled because you don't want to interrupt yourself while you're trying to handle the interrupt. So we're going to block off automatically all the other interrupts from happening. The value of the program counter is then put on the stack. So just like when you call a subroutine, the same thing happens here. We put that program counter on the stack so we know where to go back to when the interrupt is finished. And then the program counter moves to the interrupt service vector, which happens to be located in line 4. And that is why in some of the code you may have seen in line 0, which is where we go on reset, there's just a go to, and it goes to line 8. That really allows us to skip over the interrupt service vector. Then in location 4, what you should do is put a go to interrupt service routine, or typically go to ISR, which will go to wherever you're going to write your interrupt service routine. You typically don't want to write that interrupt service routine right there at location 4. You generally want to be able to just have that one line of code to go to the interrupt service routine and then put the service routine somewhere else in code. You make sure you put a go to, not a call. That is very important. That's why that is italicized there. Go to, not call right there. Because if you did a call, then what would happen is you would have the program counter once again loaded on the stack, and then when you try to return, you'd have two different addresses on there. You'd really have a stack problem, particularly if you were inside of another subroutine when you got interrupted. And so then you're going to end the interrupt service routine with RETFIE, which is a special type of return from interrupt. So this works exactly the same as a return statement, with one exception. That also will re-enable any of the interrupts that you had enabled before. So it's just like return. It's not going to put any value into the W register. So it's not like the return with literal and W, but it does return and it does re-enable interrupts when that happens. So what happens in the interrupt service routine? Well, that really is just designed to handle whatever the interrupt event is. So if you have a timer set and that timer goes off, what are you going to do after that timer goes off? So if you happen to be cooking some type of a meal and you had a timer for whatever you were baking, then your interrupt handler would say, oh, well, my timer's going off. Let me go in and check whatever it is I happen to be baking and see if it's done, and if so, pull it on out. So normally you could think about setting a timer and then going about your business in your home, but then when that timer goes off on your oven, you do want to address that immediately, or as close to immediately as possible, because no one wants to burn their food. Whereas, you know, if you didn't have that on, you didn't have that particular process going in your kitchen, you normally would just go about your routine anyway. So one of the things that's important when you do have an interrupt service routine is it's a good idea to store your values on your ports and your W register. And the reason for that is that within your interrupt service routine, you might be doing some arithmetic operations, you might be doing some checking, and that could very well change your value of your W register or any of your other ports. And so you want to be able to seamlessly go back to wherever you were before that interrupt condition. So storing a copy of W and your ports and anything else such as the status register allows you to get back to where you were before. So the status register might be important in case you happen to be checking the carry bit or the Z bit somewhere in your logic, or if you need to even change banks within the interrupt service routine in order to address the interrupt. So then you should, if you have more than one interrupt, you should do bit tests to see which of the flags has been raised. So that allows you to know which interrupt actually triggered this particular interrupt, so you know whether it was a timer or a port change or something else. And then you have the code there to do whatever you need to do to handle that particular interrupt event. So in the case of a fire, that would be go outside, wait, and then come back. And then you have the RETFIE at the end of the interrupt service routine. So let's talk a little bit about some of the registers that are involved in using interrupts. The INTCON is the main register you need to know, and that stands for Interrupt Configuration. Bit 7 is that global interrupt enable bit. If you want to use any interrupts at all, that bit has to be set to a 1. So no matter what else you do in there, if that bit is set to a 0, none of the interrupts are going to be able to trigger. Bit 6 enables some of these peripheral interrupts. We're not going to talk in too much detail at this time about what those peripheral interrupts are, but you have a whole separate 2 registers that deal with peripheral interrupts. And then T0, i.e. it's important to note that that is a 0, not an O, is the timer 0 interrupt enable. And that allows you to use a timer, and when that timer overflows from FF to 00, then you can trigger an interrupt there. You also have an INTE bit, which enables an interrupt corresponding to pin RB0 or port B bit 0. You also have an RBIE, which is your port B change interrupt enable, and that allows you to look at any other bits, including RB0, but any other bits of port B. We'll talk about that in a moment. And then you see the 3 flags corresponding to when those interrupts might be triggered. So if timer 0's interrupt was triggered, then you would go ahead and see that flag raised there. If the external interrupt, RB0 interrupt, was triggered, then you would see bit 1 go high, and if you had the port B change interrupt triggered, then bit 0 would go high. So PIE1 and PIE2 are registers associated with those other peripheral interrupts. We're not going to talk in much detail about those right now. They allow you to do things like communication, analog to digital, using some other timers that are on board, and then if you have rights to things like the onboard EEPROM, and they also help us to figure out if there's some error conditions on the board. So we're not going to talk about those in detail in this lecture. This is really designed just to give you an overview of interrupts in general. But once we start learning about things like serial communication, analog to digital conversion, and how to do those, we'll talk a little bit more about what the interrupts enable us to do compared to using some other methods. And so there are 7 interrupts in each of PIE1 and PIE2 for a total of 14 peripheral interrupts. The flags for those are in PIR1 and PIR2. So again, we're not going to focus on those right now, but the flags and the enables happen to be in separate registers for these peripheral interrupts. So here is figure 14.7 from the data sheet for the PIC16F887, and this shows a little bit of the interrupt logic. So over here you have an AND gate that determines whether you're going to interrupt the CPU at all, and you'll notice that's ANDed with the GIE bit. So if GIE is set low, doesn't matter if you have any of these interrupts over here at all, it's not going to interrupt it, because the GIE determines whether interrupts are enabled at all. Then over here we have our timer 0 interrupt, we have our external or RB0 interrupt, you have your port B change interrupt, and then you have the peripheral interrupts. And you'll notice we are ANDing that with the enable pin. So if you do not enable a particular interrupt, no matter whether it would be triggered, whether that flag would go high, it gets ignored unless it is enabled. And so here we see several of these peripheral interrupts. They deal with things like serial data transfer and memory. We're not going to talk too much about those right now. And then over here, this is your PORTB change interrupts and flags. And so if you happen to set, say, IOCB 0, or sorry, if you happen to set the IOCB 0, then that will enable a change, and then when that particular pin does change value, you will get an interrupt. We'll talk about that in just a few slides. So the RB0 interrupt, sometimes called the external interrupt, you can read about on the data sheet on page 224, or section 14.3.1. And in order to enable it, obviously you need the global interrupt enable pin set high, and you also need the INTE, which is in INTCON bit 4, in order to enable that particular interrupt. And you can choose whether you want it triggered on a rising edge of the port B bit 0 or a falling edge, and that triggering is selected using the option register in bit 6. So if you make that a 1, then the external interrupt will be triggered on a rising edge, that is a 0 to 1 transition of port B bit 0. If you make it a 0, then it will be triggered on the falling edge. PORTB change interrupt is in INTCON bit 4, and that allows you to trigger an interrupt when any of the values in port B happen to change. And so in order to know when those change, that only applies to inputs there. So those inputs have to be configured properly in TRISB. If you have a pin set as output, it will not interrupt when you change that particular output. And the bits that are used to trigger that interrupt are set in the IOCB register. So the IOCB register works bitwise to determine which of the port B values could change and then trigger an interrupt correspondingly. And the flag for that is named the RBIF flag, which is in the INTCON register bit 0. The timer 0 interrupt can work two different ways. It's an 8-bit interrupt, and so it allows you to either count up to 255, or and so it can either count clock cycles or external events. And so if you want it on external events, then you would have to have whatever that event is corresponding to bit RA4. So that could be every time someone walks into a room that has some kind of a counter, every time they trip a particular sensor, it could be every time they push a particular button. In that case, you're just counting that up, and once you reach a certain number of events there that have happened, then you might have an overflow, and that will allow you to know that you need to then handle it. Otherwise, you can configure it to count clock cycles and effectively set up something that has more uniform timing. And so this interrupt can be enabled to trigger on the overflow from FF over to 00, so it has that 8-bit count to it. And you enable that with the T0IE bit, so that enables the timer 0 interrupt. There are some other timers available that are bigger than 8 bits, so if you need to time a longer event, you can do that. And the flag for this is in the T0IF bit, which is in INTCON bit 2. So how do you configure the timer 0 interrupt? A lot of the configuration, other than just enabling it using the GIE and the enable bit for that particular timer, you need to learn how the option register works. So previously we've talked about the option register for your external interrupts, and now we can also think about this register being used for your timer 0 interrupts. And so in option register bit 5, that allows you to determine whether your timer 0 is going to increment based on clock cycles or based on some external event. Those would be rising edges or falling edges on port A bit 4. And so to determine whether it's rising or falling edge, you can use the option register bit 4. And you also may want some kind of a prescaler so that you don't count every clock edge or every button press or whatever it happens to be connected to the external, but you may want to scale that down. And so you can use the PS, which is in the option register bit 0 through 2. That's your prescaler, which will allow you to slow down the timer so that it doesn't count every clock cycle but only counts every so many clock cycles. So as a summary, let's think about when you could use some of these interrupts. So external or port B change interrupts could be used when you have some kind of a push button. Let's say you have a video game controller or you have a button on a keyboard or keypad and you want to handle those whenever somebody happens to press a button, then you might use that. If you have your gas level low, you might just have some type of a digital sensor connected to your microcontroller, and then that interrupt could be handled right away when you are running low on fuel. You might also have an alarm system, and so if it detects an intruder, then you do have a change on the port relative to its neutral setting, and so you would want to handle that right away, set off your alarm or what have you. And then the timers can be used either to track a number of items that have happened, whether that be people walking into a room or button presses or what have you, but it could also count clock cycles, which allow you to keep track of time. So in the case of a timed process, if you want something to last 30 seconds, then you could set up your prescaler and your initialization appropriately, and then after 30 seconds the interrupt would happen and you could handle that appropriately. So that's a timed process. You might also have an application where there's limited access, where you can only fit so many boxes in a room or so many people in an auditorium or a stadium, and so you might have a counter that keeps track of how many people have come in and then might limit the access if there's more than that many people in the particular building or room or whatever it happens to be. And you also might think about manufacturing settings. So if you're trying to track how many items you have made, then you might have a trigger once you meet a particular goal, or if you happen to have a certain number of defects or something like that, you might want to count those defects and keep track of that, and when you have so many, then you might want to shut down the line so you can make sure that there's nothing wrong with the production line. So in summary, interrupts allow us to handle a specific event right away. So instead of just executing code normally and polling and waiting for a particular event, you just say, hey, when this event happens, I want to handle it right away. And when that does happen, your program counter gets shifted over to your interrupt service routine, and the vector for that is in memory location 4, where you will have a go to your ISR code, which is somewhere else. And when you finish with the interrupt, you should restore the values that you may have stored, the W register and the other ports and any variable values that may get modified within the interrupt, and then you should have an RETFIE. And we'll talk more about timers in the next lecture.